Okay, today we're looking at a few more problems involving relative velocity analysis. So from last time, let's recall that our equation for the relative velocity of one point on a rigid body relative to another point on that same body can be written like this. So the velocity of B relative to A is that cross product, the angular velocity crossed with the position vector B relative to A. Now, and we also remembered that taking these cross products was pretty easy because of the fact that the position vectors only have I and j components. They only exist in the xy plane, and all our rotations are about the z-axis. That's a limitation of planar motion. So for that reason, omega is always going to be either positive or negative about the z-axis. R is going to only be I and j, and so the only cross products we have to remember are that k cross I is j, and that k cross j is negative I. We look at a wheel as being an example, a simple example of a body that's undergoing both translation and rotation simultaneously. And an important thing here to remember is that when the point on the wheel is in contact with the ground, because of the fact there's no slipping, and of course the velocity of the ground is equal to 0, that means that the velocity of point A is also equal to 0. And so if I wanted to find the velocity of the center point, I can use the relative velocity equation starting at point A, where we again know that the velocity is equal to 0. In this case, omega is clockwise, so it would be negative omega k. The position vector, where is C relative to A? Well, it's the radius r directly above A, so that would be the positive j direction. So minus omega k cross rj. K cross j is negative I. That cancels the negative sign out. And so we find that the speed of that center point is r times omega. And of course, it's going to be in the x direction. Another example problem, let's look at a 4-bar linkage. So in this case, we'll say that we know we're being driven at a velocity, an angular velocity omega of AB. And so for a given angle, theta A, can we find the angular velocity of BC and of CD? So the first step in that, we always have to find the position and do the position analysis first, because you need to know what the angles are so that you can write those position vectors of B and D. Then, since we know that we start with a velocity of 0 at A and we know omega AB, we can find what velocity of B is using the relative velocity equation. So in this case, velocity of A again is 0. Omega AB is known, and the position vector is known, so therefore we can find the velocity B directly. However, when we write the equation for velocity of C starting at point B, well, we find we've got too many unknowns for that. So we can write the equation for the velocity of C. We do know velocity B, but we don't know what omega is. But we can also, point C is also on member CD. So we can write a second equation for the velocity of C starting at point D. And of course point D is fixed, so its velocity is equal to 0. So now that we have two equations for the velocity of C, we can set them equal to each other. And so the only unknowns here are going to be the two values of omega. And again, this is a vector equation, which means two scalar equations can come out of that for plane motion, and so we can solve for the two unknown angular velocities. So next time we'll look at one more method for doing the velocity analysis. Any member that's undergoing both translation and rotation, that is general plane motion, can be thought of as rotating about a single point. Now that point changes, that's why we call it the instantaneous center of zero velocity, or I like to call it the instant center for short. We'll get to that next time.